All right, let's dive into this explainer. Today, we are unpacking the absolute heavyweight champions of oxygen-containing organic compounds, alcohols, phenols, and ethers. Let's get right into it.
So, to kick things off, I want you to think about this. What do hand sanitizer, aspirin, and, believe it or not, explosives actually have in common? It sounds like the setup to a really weird joke, right?
Well, the punchline is that they all rely heavily on oxygen-containing organic compounds to do their specific jobs. Literally, without these unique molecular structures, none of these completely different everyday products would even exist.
Okay, here's our roadmap for today. We're going to look at the oxygen family tree, meet alcohols, phenols, and ethers, put them all together for a chemical showdown, and then wrap up with their real-world impact.
Section 1. The oxygen family tree. Meet the oxygen-containing organic compounds.
So we already know organic chemistry is fundamentally the chemistry of carbon compounds. But when you attach oxygen to that carbon backbone, boom, you unlock entirely new families: alcohols, phenols, and ethers. These guys are the absolute essential building blocks for industries, medicines, perfumes, fuels, plastics, disinfectants. You name it, they are vital to it.
Moving right along to Section 2. Alcohols, the versatile cousin.
So, what exactly makes an alcohol an alcohol? Basically, it's an organic compound containing one or more hydroxy groups, that's an oxygen and a hydrogen, attached to a saturated carbon atom. The absolute simplest memory trick? Just think OH on an alkyl carbon, which gives us that classic ROH formula. Just as a quick refresher, we classify them based on the carbon they're attached to, right? Primary, secondary, or tertiary. And the IUPAC naming rule is beautifully systematic. You just find the longest chain, swap out the alkane's E for an OL, and suddenly methane is methanol.
Now, this brings us to a really fascinating macro versus micro effect. Because of that highly polar OH bond, alcohol molecules form super strong intermolecular hydrogen bonds. They just love to stick together. And that microscopic clinginess is the exact reason why they boast such high macroscopic boiling points and dissolve so incredibly easily in water.
When it comes to synthesizing them, one of the most common go-to methods is alkene hydration. You just start with an alkene, introduce some water for a hydration reaction, throw in an acid as a catalyst, and the whole thing yields your resulting alcohol, like turning ethene into ethanol.
All right, Section 3, phenols, the aromatic ring. While standard alcohols stick their OH group onto a regular carbon chain, phenols completely change the game. Your memory trick here is OH directly on benzene. That aromatic ROH structure is a huge deal because the oxygen is interacting directly with that ring.
And what's absolutely fascinating is how this slight structural shift totally rewrites their chemical behavior. Regular alcohols have a weak acidic nature. They'll pretty much ignore a strong base like sodium hydroxide. But phenols, they are noticeably more acidic and will react readily with NaOH. Why? Because the resulting phenoxide ion is resonance stabilized. That benzene ring basically acts like a shock absorber for the electrical charge.
On an industrial scale, we actually prepare this slightly edgier cousin using the Dow process. It's an elegant three-step sequence. You begin with chlorobenzene, react it with sodium hydroxide under some pretty intense conditions, and finally extract your pure phenol.
Next up, Section 4. Ethers, the oxygen bridge. Okay, so if alcohols and phenols leave their OH group kind of dangling out there on the end, ethers trap that oxygen atom right in the middle. The memory trick here is to visualize an oxygen bridge between carbons. That gives us the classic ROR structure, connected to alkyl or aryl groups on both sides.
And let me tell you, this oxygen bridge completely flips their physical properties upside down. Because the oxygen is trapped between carbons, ethers totally lack the strong hydrogen bonding we just saw in alcohols. Weak hydrogen bonding means their boiling points just plummet, making ethers highly volatile liquids.
To make them in the lab, chemists rely heavily on the Williamson ether synthesis. It's kind of like snapping chemical Legos together. You take a sodium alkoxide on one side, react it with a haloalkane on the other, and boom, they snap together to yield your synthesized ether bridge plus a sodium halide byproduct.
Section 5. The chemical showdown, comparing the three cousins.
Now that we've met the whole family, let's put them head to head. Looking at their functional groups, the differences become super stark. In terms of acidity, ethers are totally neutral, alcohols are weak, and phenols take the crown as the most acidic. Hydrogen bonding is strong in both alcohols and phenols, giving them high boiling points, while ethers have weak bonding and a really low boiling point. And water solubility? High for alcohols, moderate for phenols, and quite low for ethers. If you're actually in the lab trying to identify these, you have a few specific tests. You've got the Lucas test, which beautifully distinguishes between primary, secondary, and tertiary alcohols based on how cloudy they get. If you think you have a phenol, hit it with the ferric chloride test. If it is, you'll see a very distinct, vibrant violet coloration. And for those stubborn inert ethers, you use cleavage by HI, strong hydrogen iodide, to literally break that oxygen bridge apart.
Finally, Section 6, Real-World Impact, Why These Compounds Matter.
We started this explainer talking about everyday items, and this is where the puzzle pieces fit together. From the ethanol in our fuels and hand sanitizers, to the phenol that made bacalate plastics possible, to the volatile ethers heavily used as historical anesthetics. These microscopic structures literally shape the modern world. It's not just abstract chemistry, it is the fundamental fabric of the manufactured world around us.
I want to leave you with this higher-order question from the source material to chew on as we wrap up. Based on the microscopic structures we've explored today, why do tertiary alcohols resist oxidation? Think back to how those carbon atoms are arranged around the hydroxyl group. What exactly needs to break for an oxidation reaction to happen? Keep being curious, keep analyzing those structures, and I'll catch you in the next explainer.